Can you guys hear me now? All right, so I'm gonna restart that. Oh. I'm gonna restart that, guys. I was just stating that I'm kind of feeling a little bit under the weather right now, and so my voice may sound very different than it normally sounds. Um, but we're gonna definitely still have some good fun and talk about galaxy colonization. Yeah, I'm a little sick right now. Hopefully, it doesn't affect my voice too much. Um, so the reason why I'm doing this particular topic is because I was thinking a few days ago about what I would want to talk about, and I ran across an article, or I was Googling, and I ran across an article talking about how much time it would take to colonize the galaxy. And it kind of brought me back to my very early graduate career when I was sitting in order of magnitude class in a group, and we were doing this calculation. And at the time, I had no idea what was going on. Um, hey, Guido. I sound like very white. Sorry. Oh man. Uh, I would definitely take that as a compliment. Too bad I can't sing like him. But so I was sitting there and I didn't know what was going on. And honestly, for that entire like class period, everyone else was like giving out suggestions on how to do the calculation, and I had no idea what to say. So I figured I'm going to redo that order of magnitude class, but with you guys. And so, of course, while I'm doing the calculation, feel free to add information. Um, or if you want to change something up, we can definitely do that as well. Planets are sources for raw material. Well, in this situation, we're going to assume that we can find planets that are by solar type stars that are habitable, or within the habitable zone of that star. So, right. We're talking about galaxy colonization. And so I kind of started the problem a little bit, not I didn't get too deep with it, but I kind of made a few simple like requirements and assumptions that we can go off of as we progress through the problem today. And they're kind of stated here, and again, guys, if you guys see something that should be added or even modified or changed, just let me know. So I kind of assumed that, and I'm going to make sure I can see the comments while I'm going through these. It's perfect. Ha! That is a good question, and we're going to do that calculation as well. Good question, Hanny. So here are my requirements and assumptions. We may only populate planets that are hosted by a solar type star. So of course we can't choose all the stars in our galaxy. We're just going to focus solely on the ones that are like our sun. 2, we will only populate a single planet per star system, making the calculations a lot easier that way. 3, maximum population per planet is 8 billion people, which is kind of around the current number we have now for the planet Earth. 4, assumed planet population increases exponentially, which is true of, well, I believe it's true of how our population increases over time. 5, a minimum of 1,000 people will board a single spaceship. Now this number, honestly, I pulled from online. I typed in what was the crew size of the Enterprise, and I think it was somewhere around 1,000, so I just chose this number. 6, assumed space shuttle population remains constant over the duration of travel. Now this is important, right? Because we're going to be seeding these planets with some minimum number of people, and so and also it's also important based on the fact that if you're on a spaceship, I mean, you don't want your population to kind of increase crazily, right? You want to keep it at a certain number. So we're just going to assume that the 1,000 people that boarded the ship, that over the course of time, the number of people that are born versus the number of people that die kind of balance out in such a way that we maintain 1,000 people. The 7th one, no free birthday. And also, Henny, that's another great question about the average distance between these stars. We're definitely going to get into that as well. Number 7, a maximum of 2 spaceships built per planet. Again, this is also for being able to make the calculation simple. We don't want the situation where a single planet can essentially make 2 spaceships at one point in time and then make another 2 another point in time. The calculations get a little bit more difficult with that. And then lastly, we'll assume space shuttles are built before the population reaches maximum. And again, this is just to make the calculation simple because, yeah, make the calculation very simple. And if you want to know why, I can always explain the reason why. It's made simpler that way, but those are our assumptions that we're going to go with. Now, so no FTL, so no faster than light travel. We can do that. And so I was gonna leave that up to us to, to be able to. That's right, no dark ages. We're an advanced society, and we can possibly, have faster than light travel. And so let's go to the document now, and I'm gonna make a quick change. And of course, you guys are free to tell me if I should modify this. But given these assumptions, I've essentially decided that the equation should be this. That the amount of time that it takes to colonize the galaxy would be basically the superposition of the amount of time it takes to populate the planets, all the planets that we're going to populate, plus the amount of time it takes for us to travel from one planet to another. Now, I want to be careful in that. So, starting here at planet Earth, right? Once we reach 8 billion people, we have made 2 spaceships, and those 2 spaceships will travel some length away to 2 other planets, right? Now, once those 2 planets reach 8 billion people themselves, they will also each produce two more space shuttles, which is totally 4 in total. And then those 4 space shuttles will travel to 4 different planets that are hosted by a solar type star. And so that's kind of the idea of what's going on here. And so we have to take that into consideration into our calculations. Until something changes, there is no FTL. So yeah, for right now, I was looking at some typical speeds of some of the satellites that we've sent out. For example, the Voyager satellites. We could probably use more realistic speeds, or we can use, space shuttles that travel at the speed of light if we want to. So yeah, it's completely up to us on what speed we're gonna travel at. But the very first thing I'm going to get to is what is the percentage of solar type stars in the galaxy? And that was a very good question. You even asked it well before, I think I was even showing the calculations for it. So to do this calculation, we're kind of using information that we've derived in some of our at least one of our past conversations on neutron stars and on figuring out the fraction of neutron stars. In this case, we're figuring out the fraction of solar type stars. And we're using the equation that we see here. The actual process that we use relies on integrating what's known as the initial mass function. And I'm not going to go into all of that today. I'm just going to use the result that we obtained from that conversation to be able to derive a fraction. And so I have to, of course, finish figuring out what the fraction actually is with this very last step, which I have not done just quite yet, which I'm going to do right now really quick. So 1 minus 0.39 which kind of seems weird to me. 1 minus 0.39 oh wait, that should be the other way around, so it won't be negative. So 0.39 minus 1. So that's a mistake on my part there. 0.39 minus 1 divided by what's in the denominator. which was what, 0.23. See if I can get this. 0.23, and I put an E, and that's a -2, minus and that is a 2239 E minus -2. All right, and so this actually gives a fraction of about 3%. Is that right? Or zero? No, it gives a fraction of 0.03-ish, which seems kind of. No, I think that sounds about right actually. Um, so let's go ahead and put that in. So I'm getting roughly a fraction of 0.03, which is kind of like 3% for my calculation here. It's actually 0.027 and some other numbers, but I'm going to round up to 0.03. So 3% of the total number of stars is our solar type stars. And of course, I've assumed though, my solar type stars are somewhere in the mass range of 1 solar mass to 2 solar masses with this calculation. Hanny, that's exactly pretty much it. The initial mass function is pretty much exactly what you state there. Give it some initial mass for your gas cloud. You can be able to use that information along with the initial mass function to determine exactly what type of stars, what will be the distribution of stars you get as a function of mass. All right, so we're going to use this to now go ahead and maybe I should typeset this so you guys can see it. All right. And so we're going to use this to go ahead and figure out exactly how many solar type stars we have in total. So we'll begin. And I don't think we've done this calculation in the past. So I'm just going to do some copy and pasting here because it makes it simpler that way. And this is going to equal. And so the total number of stars in our galaxy is somewhere in the order of 100 billion stars. 100 billion stars. So we're going to go with that, which is, what is that? 10 to the 11 stars. So we have 10 to the 11 stars. And of that, 3% of them will be solar type, as I've defined to be solar type, being somewhere in the mass range of 1 to 2 solar masses. 11. We're multiplying this times 0.03. So 0.03. Let's see if you guys can see that. All right. And so from here, that's just going to be simply 3 times 10 to the 9. So basically 3 billion stars. So 3 billion stars we have that are solar type. All right. So now that we have that number, and Hanny brought up this very good question of, well, how far apart are, well, how far apart are they spaced, right? So we can actually get at this number by using the density of these types of stars. Um, to do so, I'm going to go ahead and calculate a density for the stars. I'm going to go ahead and calculate a density for the stars. And to do this, we're going to have to use the volume of the Milky Way galaxy. Well, this number we just derived for the solar type stars divided by that volume. And then we could take it a step further to figure out the physical separation between the solar type stars. So let's go ahead and do that first. So what and unfortunately, you guys cannot see what I'm typing right now. Maybe that might be best if I can show you guys what I'm typing. Let's make that quick change, actually. So let's add another window. I'll just call it tech, and then we can miss. And let's shrink that. So this is the window that I'm using to input the information into the PDF. There we go. Now I'll just put it down here and increase the font size in just a second. All right. And so I probably should even also add to this what exactly the calculation is below. So this is the number of solar type stars. And this next one is going to have to be going to deal with calculating the interstellar distance between these solar type stars. All right. And I will try to make sure that I'm keeping up with comments too. And if what I'm saying is not making sense, guys, let me know. All right. So the very first thing we're going to want to do is calculate the density. Some density value. Or maybe I can probably get past this. Not actually a mass density, but more like a number density. Some number of stars per unit volume. And then basically what you do is you'd basically take the reciprocal of your number density to get total volume covered per star. So let's just go ahead and solve for that actually. And hopefully what I'm saying is making sense. Does it matter that the Milky Way is a disk instead of an orb? Well, with this particular calculation, I'm kind of assuming that it's spherical in shape. So yeah, it does matter. It does matter the physical shape of the galaxy, but with this calculation, I'm kind of assuming that it's spherical because my density is going to be dependent upon or the volume within my density is going to be dependent upon the volume of a sphere. All right. And so what I'm calculating here is 1 over the number density. So 1 over n. And hopefully what I'm saying here makes sense what I'm getting at here. So 1 over n, and this is going to be solar stars. And we can state this is going to be equal to the volume of our galaxy divided by the number of solar type stars. And because I like to copy and paste, I'm just going to copy and paste this information. That goes in the denominator, and up top, we have the volume of our galaxy. All right. Okay. Starting to think now. Is this how I really want to do this? If I do that, this does give me a density of stars, and I can use that density. Yeah, I think this is the correct way of going about doing this, actually. Now, again, guys, I'm kind of doing this like right here and right now. This is all live, so whatever mistakes I'm making this is going to be made here. And if you guys catch them, by all means, let me know. Like, Matt, that doesn't make sense. Because I'm constantly looking at your comments on the side here. All right. So the volume of the Milky Way. We can continue our calculation here. And so really what this is going to give us, given that I have 1 over the number density, it's kind of going to give us a volume per unit number. Or the volume that encompasses one solar type star. So Hanny states here, since 2 ships leave each planet, will this be like a chain reaction? You could think of it like that, actually, right? You could think of it as like a binary tree, if you wanted to. Or like a shower that's, that's binary in nature. So the very first planet, us, makes 2. Then those 2 makes 2 more. So, all right. So the volume of the Milky Way. That's a great question. What is the radius of the Milky Way? So we have to use fraction. This is going to be 4/3 pi. And because I want to reduce this as much as possible, and I won't do that yet, actually. I'll wait to do it. So we have 4/3 pi, and then we have the radius cubed, and this is the radius of the galaxy. And then, of course, this is going to be over 3 billion. So 3 times 10 raised to the 9 stars. All right. So to get this R, we need to understand exactly what is the physical radius of our Milky Way. I think it's somewhere on the order of probably like around 15 kiloparsecs. Somewhere between 10 to 15 kiloparsecs. Because I know this the sun sits at 8 kiloparsecs. But I don't want this, of course, in units of parsecs. I want it in more physical units. Ah, thank you. we'll use that. So a diameter of 100,000 light years, which is a radius of 50,000 light years, and we can of course convert this um, by, and this is a unit of distance, of course. So let's do this. Let's go ahead and do 50,000 light years. We want to convert it to units of probably like meters. And so we can actually do all of this within the equation. So left, right, 50,000. It's 5 times 10 to the 5. Or wait, 5 times 10 to the 4. It's up with me right now. 5 times, and we have 10 to the 4. This is in units of light years. So we actually have to convert this now. All right. And hopefully you guys can see that as well. I think so. Yeah, all right. And Hanny, thank you for you're giving some really good information here. I hope I'm not boring anyone here. If I am, by all means, join the conversation. If you have any questions, I'm more than happy to answer. So we have to convert light years, of course, into a more physical unit. Or not a more physical unit, but something that's a little bit... I like to work in SI units. So we're going to convert to meters. And I'm not going to waste much time, actually. I'm just going to go online and find a converter. So let's say light years to meters. So that's like 9.5 times 10 to the 15 meters per light year. And I'll go ahead and add that in here. Now, typically when we did these problems in order of magnitude class, we had to use the information that was already available within the group. So I'm kind of cheating here by going online and finding out, conversion factors. But I don't want to get stuck at this portion of the problem with this. So that's per light year. All right. And I think that that's good to go. All right, so like in order of magnitude, I'm going to go ahead and start canceling things out that I know can, kind of essentially be rounded off to 1. Prime example, the 4/3 pi. I mean, in all honesty, the pi and the 3 are kind of very close to one another in value. So those can be rounded off to 1. And also, the 4 in the numerator and the 3 in the denominator are kind of very close to being equal to one another. Or their ratio is almost equal to 1. So I'm going to cancel that off as well. And so I'm kind of really left with that 5 times the 9.5. Which for all essential purposes, I'm going to round the 9.5 to like 10. Making that 10 to the 16. So 5 cubed. So 5 cubed is 225, I think. 225. And this is times wow, that looks like that's gonna be a really big number. All right. So 10 to the 16, 10 to the 4, 10 to the 20. What? Oh, well, this is in meters, though. Okay, never mind. That makes sense. All right, so 10 to the 20. 10 to the 20 cubed is 10 to the 60. And that minus the 9, 10 to the 51. So times 10 to the 51 power. And this is in units of meters. Okay. Oh, Larry had a question. I'm sorry. uh, let's see. Larry had a question about brown. Oh, okay. Let's see. So typically, whenever you're talking about the production of stars, the less massive star will more than likely be, its population will probably be higher than the more massive star. So I'm trying to remember which of these two stars is the least massive star, and I think it might be the brown dwarfs. Is that correct, Larry? I think the brown dwarfs are their mass range is smaller. In general, is their average mass is smaller. Yeah. For example, G-type stars or solar-type stars will greatly outnumber, for example, like O or B-type stars or A-type stars. All right, let's see. So I think this is good. I think this is good. So light years. This should be meters cubed, actually. And so this is kind of where we can get at that distance I was talking about. So this is meters cubed. Yeah, exactly as Hanny states. Um, the more massive main sequence stars, they go quickly, and eventually the gas they let out into the universe, it gets reused. Let's see, and that should be that. It should be meters cubed there. So this is meters cubed per solar type star. Um, all right. And so what I can do with this now, right? So this is the volume that the way in which we should think about this is that this is the volume, and kind of at the center of this spherical volume is one star, one solar type star, and we want to be able to extract the radius from this. So naturally, what you do is you'd equate this to equal 4/3 pi r cubed, where the r in this case is the radius of the sphere that encloses a single solar type star. And so I want to make sure that that's clear, that we're not mixing r's here. So here I'm going to put Milky Way. And so down here, it's going to be a little bit different. And in all honesty, of all the courses I've taken, in school, period, at all levels, order of magnitude was probably the most class I had the most fun in. And so no indent, distance between solar type stars. And so what we do is now say 4/3 pi r cubed continued. 4/3 pi r cubed. And now we're just going to say solar type stars, solar star. And this is going to be equal to the number we just calculated. And again, I'm going to go ahead and, use, let's make sure you guys can see that too. All right. And I don't want to lose comments. So the brown dwarfs are in between planets and main sequence stars. And I mean, it would make sense for their Goldilocks zones to be very small. That region of where you can have liquid water, given those really small dim stars, should be much smaller. Let's see. All right. So again, I'm gonna simplify this so that the pi and the 3 cancel. But I can do this. I'll take that, put that there, and then I'll divide by 4. I'm seeing that this problem is taking way longer than I expected for it to take. I figured I would just blow through all this, but I mean, I'm typing it up as well, so that's what's slowing it down. All right. So 225 divided by 4. It's probably not a bad number at all to get. 56.25. And I'm going to eventually take the cube root of all of this. So let's do that actually. So R and equals. And so what I'm going to do here is, you can't see it unfortunately, but I'm going to do the cube root of both sides. And so essentially what I have is, what was that, 225 times, or E 51. I can divide this by 4. And I can raise this to the 1/3 power. And I get 3.8 times 10 to the 17, essentially, meters. And I'm kind of happy to hear that number because as of right now, the average distance between stars is roughly around a parsec, which is, I think it's like 3 times 10 to the 18 centimeters. So this value, I don't think is too bad. 3.8 times 10 to the 17. I think it makes sense to me. And so that's actually a way that you can go about calculating the distance between objects. You could take you could take the number density of that particular object, take the reciprocal of the number density. Once you have that value, you can equate it to the volume equation and solve for R. And that would give you the mean distance between those objects that the density corresponds to. All right, so we have a distance between the solar type stars of roughly like 4 times 10 to the 17 meters, and we have their total number. All right, so with that information, we can now continue on with the rest of our problem. All right, so Hanny's asking, does the center of the galaxy hold old or newer stars? Oh man, hey, that's a great question. Off the top of my head, I don't know, but if I were to think about it, my thoughts would be that the center of the galaxy probably has the most massive stars. Um, they'd naturally be attracted to the center because they're more massive, more gravitation or stronger gravitational forces are at play, and because they're more massive, um, they'd probably die sooner. Hmm. I honestly don't know. That's a good question, Hanny. That's a very good question. And one that I'm now going to actually look up eventually and figure out the answer to. So Hanny asks, if we sent self-replicating probes, it would be interesting to see what they look like when they came back around. Hope they haven't turned evil. I don't know. I mean, I guess that it depends on how they would define evil, right? If they go around and there's life elsewhere, and we haven't really defined evil for those probes. You know, I mean, we'd have to define evil for them, and then see exactly, and they'd have to understand what evil is, and see if they come back and are displaying evil traits or something, because they might be doing something that they find to not be evil, and we might find it to be evil. All right, so mean distance, right? So we have to get back to the problem, and I'm sure I am not going to finish this. This is probably something that I'm going to have to do like outside of the stream finish, and then we can continue the discussion. But let's see. Hmm. So we know the distance between the solar type stars. We know the number of solar type stars. So now we could probably start getting at some of this other information. For example, the time to populate the planets. We can actually do this without this information, actually. So it's exponential, right? It's an exponential function. So let's go ahead and write that down. So no indent. Now the information that we've calculated is important. So Hanny had some good questions, and this information will be important for the calculation. Let's see. So we want to figure out time taken to populate a planet. I'm so trying to like hold back that urge to start coughing uncontrollably. Okay, so what would that be? So population p as a function of time has to be equal to, and it's exponential, so in some initial population value, p sub 0 times e raised to the t power, where in this case t is time. All right. And I think that this should work just fine. But just to be safe, I want to make sure that this is actually a legitimate equation to use for what we're doing here. So exponential growth. I'm actually going to Wikipedia really quick, and I'm going to look up exponential growth and see if I can find an equation for it. Again, guys, we're kind of doing this on the cuff here. All right, so exponential growth. Let's see what we can find here. I'm seeing. So actually, there is an equation here, and I'm looking at the Wikipedia article for exponential growth, and it states the formula for exponential growth of a variable x at the growth rate r as time goes on in discrete intervals. Okay. Um, X of t is equals, or x is a function of t is equal to x naught, or the initial number of the population, times 1 plus r quantity to the t power. Hmm. Trying to see if I can find one that's, or better yet, what is the, so actually let me look at what you guys are putting here before I continue. So people, 1,000 people, and it takes 20 years to grow a kid. So Hanny states here, so 1,000 people, and it takes 20 years to grow a kid. Some old, but also some very young stars, according to this. Thanks, Finmill. Oh wow, is the presidential message thing going out too? Okay. I'm happy that I'm not, being affected by that. Oh, I see. Yeah, I want to be able to find an equation that would make this so much easier. Given some initial population, um, and knowing that the population will grow exponentially, how much time would it take? And basically, what you do is basically what I wrote earlier. I think let's actually. You basically, I think you'd have an equation like this, and you'd solve for t, which would require taking well, dividing both sides by the initial population size, which is p sub 0, and then taking the natural logarithm of both sides to essentially get t by itself, to extract the t from that exponential term. But I'm not too sure if this is the exact equation I want to use, which is the reason why I'm looking up exponential growth right now. With the equation I just saw, we'd have to assume a rate of growth. And now that I think about it, I don't think my equation is completely correct. Or maybe it is. Um, KT, that's what I'm missing. So we actually do have to assume a growth rate, which is what you were getting at. That's exactly what you were getting at, Hanny. So we have to modify this equation. It should be RT. And so this equation would work. And to solve for the amount of time it takes for the and we know P in this case, right? Or we know we know P max, what P max should be. We're 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 growing our population to 8 billion people. And we're seeding the population with 1,000 people. So P naught is equal to 1,000. P, or in this case, I should say P max. So let's actually modify that. So max, this is the maximum we want. So P max should correspond to time max. And we can solve for that time by using, I'm not going to go through all the math, but basically you divide both sides by p sub 0, and you take the natural logarithm. And what that should give us is that RT max is equal to, so it's important that we actually have a rate. The natural log. I'm actually really liking doing this now. I wasn't able to enjoy it, like I said before. I wasn't able to enjoy it when I first did this problem so very long ago because I didn't know what was going on. Everyone else was just, was just blazing through the problem and understanding things, and I was just sitting there just nodding my head. Let's see. How do I want to do this? This. And given the timing, I'm definitely not going to go over 130. I might end up finishing the problem offline and then presenting the solution once we come back. Once I come back on Friday after Daily Space. And so we can make this one divided by p sub 0. And guys, and I know you guys said that it's not boring you, but if I am boring you guys, please let me know. Because I want you guys to enjoy, doing science and enjoy our conversations. Let's see. I think that's. And I could put this in a fraction. This is over the rate. So we actually have to come up with a rate. I think this equation is what would work for us. Where we know P max and we know P sub 0, but we don't have a rate quite yet. And someone was already getting at a rate. Well, as far as the rate's concerned, we can assume a rate. We don't have to have a functional form for it. And I think you were saying something earlier, actually. It takes 20 years to grow a kid. So, do we want to assume that So let's think of it like this: how many kids are born in a single day? And we can actually, we can just look that up online. And I'm going to assume whatever rate we find online, it takes into consideration, or the population rate, whatever population rate we find online. I think it probably would take into consideration people being born versus people dying. And given that our population is growing, of course, I think it's fair to assume that the number of births greatly outweigh the number of deaths. I am so sorry to hear that about your cats, Finmeal. I don't even know the reason why they were doing the alert in the first place. Ah. Yeah, people die, unfortunately. Hopefully one day, well, we've actually increased, the average, life expectancy, right? With the advances in medicine and technology. All right, so according to you, okay. Let's see. So wait, Finmil, are you saying that that's I'm not too sure what that is. Let's see. UNICEF. Let's see what is that. So I'm looking up. I don't know if it's an acronym. I think UNICEF. Wow, that is a lot of kids. 3.5 times 10. Okay. All right. This is what we're gonna do actually, because I'm seeing that it's now 1:30, and I'm really loving the problem that we worked. What we got into so far. Um, we're gonna pick up where we left off, and I'm gonna write these values down. We're gonna pick up where we left off, or where we're leaving off right now. We'll pick it back up on Friday, and finish off the problem. Um, right now my nose is really stuffed. This is also part of the reason why I'm trying to get off right now, because it's kind of difficult to breathe right now. But guys, I enjoyed the problem, and I'm loving where we're getting with this problem. So I will see you guys on Friday after Daily Space. And again, thank you guys for thank you guys for hanging out with me. Thanks, Mr. White. Thank you guys for hanging out with me, and I will see you guys Friday after Daily Space. All right. Okay, bye.